Essentially, what happened before the Big Bang? You have to be careful with the language. You define the Big Bang really carefully as the time when the universe was very hot and very dense. Likewise, as stated, that cannot be disputed, because we can see it as we look out. Our preferred explanation for how the universe got into that state is that there was a time before that, okay? And it's called inflation. What existed before the Big Bang? This question has always been a difficulty for scientists, but now it seems they have found the answer, and it has left scientists shocked. As Brian Cox revealed that a terrifying event existed before the Big Bang. So the idea is the universe was, in a sense, cold and empty. It's expanded extremely quickly. That growth then slowed down and stopped, and the energy that was driving the expansion got dumped into space, warmed it up, and produced all the particles out of which were made. That's what we call the Big Bang dot. So what existed before the Big Bang? Why has it frightened scientists? Let's find out. That theory has an extension called eternal inflation, which proposes that inflation essentially goes on forever. It just stops in little patches. So imagine stretching the fabric of the universe. Space-time stretches, stretches, and then it slows down and stops in little patches. Each one of those patches is essentially a massive explosion, a universe of which ours is one. You end up with a picture like this, an infinite, fractal universe, basically a limitless number of large bangs. And that's called the inflationary multiverse in the vast cosmos. The idea of absolute nothingness seems theoretical rather than real. Even if all energy were removed from the universe, it wouldn't be truly empty currently. The universe is full of matter, radiation, antimatter, neutrinos, dark matter, and dark energy. Even without energy, the universe still creates new forms of energy. This phenomenon perplexes us. The universe doesn't understand our concept of complete emptiness. If we removed all energy, leaving a void, one might expect the universe to reach absolute zero with no particles, yet that's not the case. Even in an empty universe, its expansion would continue to emit radiation, extends far into the future or even back prior to the violent Big Bang. The universe, it appears, never truly becomes void. Given all of this, is it plausible that the universe originated from nothing? We can guarantee that something always persists. Even if particles, antiparticles, photons, and quanta are removed, empty space remains. If we move away from any sources of mass or energy, clear the space of external electric fields, magnetism, and gravitation, and prevent photons or gravitational waves from entering, a kind of physical emptiness still exists in this space. Quantum fields endure, and the fundamental constants and laws of physics last because of an inherent, finite, positive, and non-zero value of zero-point energy. This represents the closest approximation to nothing in our universe. You might envision an even more nothing-like state, but it lacks physical reality. No experiment can replicate such a condition. Right? Adhering to scientific principles, we acknowledge that something always exists, because true nothingness cannot coexist in our universe. Yet the question of why remains unanswered by science. Currently, our universe appears far from empty. It's teeming with stars, gas, dust, galaxies, quasars, cosmic rays, and radiation, both from starlight and the remnants of the Big Bang. With improved observational tools, we could potentially detect additional signals we anticipate will be present. This includes gravitational waves generated by any mass moving through a changing gravitational field, mysterious signals from the constituents of dark matter, and a broader perspective on black holes, both active and dormant. Aside from those emitting the most radiation, this is the cause of everything we see in a universe that isn't static, but is continuously changing. From a physical standpoint, it's intriguing to comprehend the evolution of our universe on a grand scale. The fabric of our universe, known as space-time, is expanding. This implies that if you position 2 points far apart in your space-time, The proper distance between those 2 points, the time it takes for light to traverse between them, increases over time. The universe isn't just getting bigger, it's also becoming colder. As light expands, it stretches to longer wavelengths, it moves toward lower energies and cooler temperatures. The universe was hotter in the past and will become even colder. In the future, during this process, objects with mass or energy in the universe attract one another to form groups, creating a vast cosmic network. If you were to somehow remove everything, all matter, the total amount of energy that would be radiated would remain. Essentially, you'd have empty space itself, still expanding, still governed by the laws of physics, and still influenced by quantum fields. This is the closest physical approximation to true nothingness, yet it still adheres to specific physical principles. To a physicist, in this reality, removing anything else would create an unrealistic state that no longer reflects the cosmos we inhabit. This suggests that dark energy, as we currently comprehend it, would nonetheless be present in this hypothetical universe devoid of matter. In essence, if every quantum field in the universe was set to its lowest energy state, we would arrive at the zero-point energy of space where no additional energy could be extracted for mechanical work, in a universe containing dark energy. A cosmological constant, or the zero-point energy of quantum fields, it's plausible that the zero-point energy wouldn't be truly zero dot as the universe continues to expand and cool. There will eventually come a time in the distant future when radiation becomes the dominant component, surpassing other forms of matter and energy, leaving dark energy as the primary influence. However, there's also a period in the universe's history, not in the future but in the distant past, when something else, in addition to matter and radiation, held dominance during cosmic inflation. Prior to the hot Big Bang, our universe underwent extremely rapid and constant expansion, instead of being dominated by matter and radiation. The cosmos was controlled by the field energy of inflation, akin to today's dark energy, but much more effective, expanding at a significantly faster pace if eternal inflation is accurate. But time remains finite. Where might the universe have originated? There must have been a beginning, correct? To address this thoroughly, let's decipher 3 frequently misunderstood concepts and discuss each individually. 1. The hot Big Bang in relation to our universe. 2. The theory of cosmic or cosmological inflation and its role in preceding and preparing for the Big Bang. 3. The issue of an ultimate beginning or origin for our universe, and why both inflation and the original concept of the Big Bang might not offer a satisfactory solution to this. Questioning the early 20th century. A significant synthesis took place when 4 key pieces of information came together. A breakthrough by Alexander Friedmann in Einstein's general relativity showed that a universe filled uniformly with energy and matter in any form cannot remain static. It must either expand or contract. This expansion's rate or contraction depends on the overall energy density in space. Henrietta Leavitt's observational work established a connection between the period of brightness and dimness of variable stars and their inherent brightness, known as the period luminosity relation. Observations by Vesto Slipher, weighing the shift in light, either red-shifted or blue observed phenomena evolved outside of our solar system. Perspective in the elliptical and spiral nebulae, which were later identified as galaxies, indicated their existence due to the fact that they were rapidly moving away from us at high speeds. Edwin Hubble, alongside similar types identified by Milton Humacense, similar to the variable stars discovered by Henrietta. Leavitt studied these elliptical and spiral forms of nebulae. This enabled them to gauge the distances to these galaxies and confirm they were beyond our own. These findings, combined with other data, led to the idea that the universe is growing. The universe expands. It suggests that, over time, space itself stretches, causing the matter it contains to become less dense. As space expands, radiation like light waves not only becomes less concentrated, but also experiences long stretches contributing to the universe cooling. If we rewind the clock the other way, the universe would have been denser and hotter. In earlier times, radiation in the universe, when it was still young, had shorter wavelengths, resulting in higher temperatures. If you envision going back as far as physics permits, you'd reach a singular state where all matter and radiation existed within a single point of infinite density and temperature. The Big Bang Theory, based on this initial concept, resulted in the formation of 5 essential expectations for the early universe's hot and dense conditions. These forecasts became the foundation of the Big Bang Theory. 1. The universe ought to exhibit expansion, as indicated by a distinct redshift relationship between extragalactic objects. 2. The universe should have been relatively uniform initially, with structures like stars, galaxies, and galaxy clusters gradually forming and evolving over time. 3. In the past, the universe was hotter, preventing the formation of stable neutral atoms. This prediction led to the discovery of the cosmic microwave background, observable today. 4. In the universe's initial stages, atomic nuclei were extremely hot and couldn't form stably, which led to the creation of light elements such as hydrogen, helium, and lithium. 5. The prediction of neutrinos. The universe was so hot that neutrinos were an important factor. This was recently confirmed. Cosmic neutrinos should have observable effects on both the large-scale structure and the leftover radiation from the Big Bang. With strong observational evidence supporting these predictions, the Big Bang Theory has remained uncontested as the primary explanation for the early universe since the mid-1960s. When the discovery of the cosmic microwave background as evidence supporting the hot Big Bang Theory began to grow, however, in the 1960s and 1970s, certain challenges surfaced that the Big Bang alone was unable to resolve. A few observations went against the concept of the universe, originating from a single condition of extremely high density and temperature. 3 of these obstacles stand out. The horizon problem, when we observe different directions. The universe seems to possess uniform temperatures and density throughout. However, since the onset of the hot Big Bang, these regions have never had the opportunity to communicate, exchange information, or achieve thermal harmony. How did they develop to exhibit such uniformity? The flatness problem in an expanding universe. There's a continual tug-of-war between expansion pushing things apart and gravitational forces pulling everything back together. Remarkably, these opposing forces in our universe appear perfectly balanced, resulting in a spatially flat universe. Why is this the case? The monopole problem. If the universe underwent extreme temperatures and energy conditions in its infancy, why do we not observe any exotic relics like right-handed neutrinos or magnetic monopoles? Theoretically, such particles should still exist. Rather than accepting these conditions as mere coincidences, scientists sought a mechanism to organize and establish these first conditions. In 1980, Alan Guth introduced an answer to these astronomical mysteries with a groundbreaking paper. He suggested a preliminary period of rapid and ongoing expansion, a phase in which the universe's energy wasn't distributed among matter and radiation, but was an intrinsic part of space itself via a field or a different method. This period, called inflation, could solve all 3 problems for the horizon problem. The uniformity of temperature and density is attributed to the past interconnectedness of everything. Inflation caused this connection to deteriorate by stretching space so rapidly that it explains the current observed state. For the flatness problem, inflation expanded the universe so much that, regardless of its initial curvature, the visible part now appears uniformly flat. For the monopole problem, inflation prevented the universe from reaching excessively high energies or temperatures that would have created these exotic relics. The maximum temperature after inflation avoided their formation. In the 1980s, inflation theory made precise and testable predictions regarding the beginnings of cosmic structure. Predictions that should be detectable in both the cosmic microwave Background and the large-scale structure of the universe. These forecasts, crafted decades ago, were confirmed by observations from the 1990s to the present day. The predictions include an almost but not entirely scaling variant spectrum of imperfections, such as differences in density and temperature. Density, irregularities that are entirely adiabatic, no energy exchange with surroundings, and not isocurvature. Not related to entropy variation. Changes on scales larger than what is signal traveling. At the speed of light in an expanding universe could generate A. It's a maximum temperature limit for the universe during the hot Big Bang. It's notably smaller than the Planck scale, because inflation involves the rapid expansion of space rather than reaching a singularity. It offers an alternative depiction of the beginning. Instead of time and space emerging gradually from a single state, inflation suggests an expansion that culminated in the Big Bang. This raises a fundamental question. Does the concept of an actual beginning of the universe even make sense? Without inflation, we could trace the hot Big Bang back to a single state in which the entire universe's size approaches zero in a finite time.